So welcome everybody. I'm glad to welcome also Aidan Hogan to Nuremberg. Aidan is an associate professor at the Universidad de Chile and a vice director of the Millennium Institute for Foundational Research on Data. I'm very glad Aidan is here today, and he will talk about large language models and knowledge graphs. Aidan, the floor is yours.
Okay, thank you, Andreas. Thanks everyone for coming, and happy Chilean Independence Day. If I were in Chile, I'd have a bank holiday today, but I'm happy to be here to present this talk. So the title of the talk is Knowledge Graphs in the Age of Large Language Models. Maybe as an idea, who here knows about knowledge graphs? Pretty much everyone, okay, maybe some people not. So this talk is maybe thought of as someone who knows about knowledge graphs, what is the effects of large language models. But those who don't know about knowledge graphs, we can cover that topic as well. Who here knows what a large language model is? Yeah, if not, maybe ChatGPT you've heard of and so forth. Okay. So in general, my area of research is the semantic web, which you may have heard of. I hear many of you have taken courses on the topic. And I was writing a book for many years. It dragged on for a long time, this book. And in this book, The Web of Data, a little bit of a plug for my book as well, I was trying to motivate why we need a semantic web. Yeah? What's wrong with the current web? So this example that I used, which was the very first example of one of the first pages of the book, is the following. Julie is a literature student. For her thesis, she needs to find a list of Nobel laureates in literature who fought in a war, the year they were awarded the Nobel Prize, and the name of the wars they fought in. So she wants to do a study on the effect of war on literature. Yeah? So how would you do this if you had to do this? So you have the web. Okay, maybe we'll leave aside ChatGPT for the moment. How would you do this? Any ideas? So you could search on the web, right? But you're unlikely to find directly a web page that gives you all the answers, right? So what you could probably end up doing, what would be a reasonable effort at this, would be to get a list of the people who've won the Nobel Prize in Literature, for example, from Wikipedia, generally a reliable source. Nice thing about the web is you have links, so you can then visit the links of the people who won. In this case, Sully Proudhon. And then how would you find out if they fought in a war or not? Not so easy. You could Control F, search for war, or conflict, or battle, or invasion, and try to figure out if you can see some information, some keywords, right? And then there's some doubt in your mind, did you use all the keywords that might hit somehow this question, right? You might find through that, for example, a mention of the Franco-Prussian War, and then you click on that because you need to find out what dates it started, what were the years of this war, and so forth. And okay, that's great. So Sully Proudhon is in the results list, and then you continue to the second person who won, and you do this for 100 and however many winners, right? So why is this difficult? This is difficult on the web, using the traditional current web that we all know. Google is excellent for finding pages. Yeah? So if somebody has written the answer to our question on a web page, we can use Google to find that web page. The problem comes when there's no one web page that has all of the answers we need, and we need to integrate data from different places. Yeah? In that case, we have to do that manually at the moment, in most cases. Yeah? So what we see is that somehow there are some tasks that are difficult on the web, and what we need is some solution to be able to address this, in particular to integrate different data and different services on the web. So what is the issue? The issue is that the web is conceived of as a formatting, essentially, structure. We have some light semi-structured data, but essentially it's mostly for formatting, where we have web pages and we can define things like titles of web pages, and we can define tables in web pages, and most importantly, we can define links, and those links will bring us to somewhere else where we'll get a description of that information and so forth. So this is principally thought of as a content vehicle for human consumption, that a person's going to read this, right? So if we look at this, we can say we can deduce all sorts of information about the people who won Nobel Prize for Literature in this case. We can click on links and we can read more information. And then we can answer questions based on this, yeah? So we can answer the question, for example, of, no. Answer the question of why PowerPoint has crashed. Let me see. Is it really crashed? Yeah. This started happening to me recently, 2 days ago. Randomly crashes. I have a PDF version in any case, but let me go back. Okay, so we can ask questions like what Nobel laureates fought in World War II. Yeah? And if we look at the content of these web pages here, we can say, okay, William Golding, we're focused here on the biography, joined the Royal Navy, Normandy invasion. William Golding is a laureate, and so he has won the prize. And the Normandy invasion was part of World War II. Yeah? So we can answer, in this case, at least William Golding. Yeah? And if we read enough pages, we could continue answering further, or generating further answers for this question. So the example I like to give to students, just to break somehow, to illustrate the difficulty of processing this automatically. The question is, why couldn't we have a machine or some sort of algorithm process this content and then get this sort of answer? Why is that difficult? Yeah. So what I do for illustration in the course, in the book, is to change all the letters one to one. Yeah. So I mapped each letter in this alphabet to another letter. Yeah? And the point is that now we've broken the semantic connection. These words don't mean anything to us. So this view is identical to this view here to a machine. There's no difference. Yeah? The pages are isomorphic in terms of there's a one-to-one mapping of letters. So processing this content from the perspective of a machine is the same as processing the other content. Absolutely, only a superficial difference. And if I were to ask you now, this question, what would you say the answer is? It's a good guess, yeah? 42. So it's hard, right? But if we looked at it, maybe, okay, we'd have some hope, probably not, that the answer is o. Yeah? So this is what it looks like from a machine perspective in terms of natural language processing and natural language understanding. This is the task that we have to solve. Would be to somehow, from this sort of content here, be able to address, let's say, questions or to integrate data expressed in natural language. Yeah? So we see that this is not a trivial task. Yeah? So instead of trying to process natural language and trying to, solve this problem of processing this sort of unstructured data, the main conceit, the main idea of the semantic web has been to use structure and symbols. Yeah? So the idea is, even if a machine has no idea about the world or what is being described, that somehow we can use, for example, a graph structure. It could be a table, it could be something else, but there's specific benefits to a graph. And we can use a symbolic approach. Yeah? We can use symbols. So here I've used symbols that are from astronomy, and this is not because you need to know what the symbols are. It's better if you don't know what the symbols are. Okay. So I have a graph that represents something, and I have some numbers and some Boolean value, because machines can do something with that. They can see it's a number. If I add 1 to this, then I get another number, so it's not completely opaque. I have a true value. But then I have all these other symbols that just represent entities, things. And then I have these symbols that represent somehow relations, what kinds of relations exist between these entities. Yeah? This is essentially a symbolic knowledge graph. And then I have this question here, or query. And here I have 2 variables, A and P. So the question is, could we figure out what A might map to? Which of the symbols here? And could we figure out what symbol P might map to? So we can map these variables to any nodes or any symbols in this graph. And we see, okay, well, this one seems to be a constant. So we have to somehow map this to this, like to like. Then we see that we have this 4-like symbol. Okay. So we could figure out that P should map to this element here. Yeah. And same here, we have this M-like symbol here, and then A should map to this upside down U. I don't know what the symbols mean either. They all mean different horoscopes and so forth. So if we looked at it hard enough, we could see that this probably maps to this, and this probably maps to this, and we can generate a mapping, which is a solution. Yeah, so we compute what's called a homomorphism from this graph here to this graph here, and we compute a solution. So we can do this algorithmically. It wouldn't be so difficult now to write an algorithm to do this. It's not so trivial either to do it efficiently, but we can see that this is something we could define an algorithm for. So this is a symbolic representation where we represent our data symbolically, we represent our questions or queries symbolically, and that allows us to get some answers back in symbols. Yeah? So what are these abstract symbols? If people know Wikidata here, maybe? Yeah. So this is an example from Wikidata where the symbols are just codes. So we have P's for types of relations, and we have Q's that represent different types of entities. And what we're getting back as a result are answers in the symbols. Yeah? So this is an example from Wikidata. Yeah? So the symbols here are just a different format. We use Q and some number to represent something, some entity, and this to represent some type of relation. And what do we see as a user? As a user who maybe understands English and has some sense of the world, we can interpret those symbols as referring to things. Yeah? So in a more readable syntax, one of the symbols here is William Golding, Nobel Literature Prize, 1983. Year 1983, type Nobel Literature Prize, accepted true. Normandy landing, Operation Overlord, World War II, war. And then we have this query here. And what does this query generate? We're asking for people who were awarded prizes of type Nobel Literature Prize. And we see that William Golding won in natural language processing. No, Nobel Literature Prize, that's a coincidence, in 1983. Yeah. So effectively, afterwards, if we apply some sort of, or we label these symbols, or we say what they mean, then the results can be meaningful, even though it's a purely symbolic approach. Yeah? So not just for queries, we can also define syntax, semantics, using, for example, rules or ontologies. In this case, we have a rule which says, if you match this pattern here in the graph, then you can infer this other pattern here. Yeah? So what could we infer based on this rule? What would this match? So we have three variables, x, y, and z. So we could say z could map to this h thing here. Y could map to the moon. And x to, I guess, Taurus, or some bull thing. Yeah? So what does that infer? It infers then this pattern, xz, which infers that Taurus must have this p-like symbol to this other symbol here. Yeah? So we infer this symbol here. So using the symbolic approach, again, we could think of an algorithm for this. That wouldn't be so difficult. And what do we get as a result? We essentially are encoding what's called the transitivity of the part of relation. Yeah? So if x is part of y and y is part of z, then we get that x is part of z. So in this case, we're adding the relation Normandy part of World War II. Okay. So this was the kind of motivation for the book, and also what I use in the course I teach in this topic about the value of symbolic representations, that it simplifies the automatic processing of data with this sort of representation. So this is all based on the idea that it's very difficult to automatically process this sort of content here. Yeah? Now there is a slight problem with this motivation. So here's an example. Probably you can guess what the problem with this motivation is now. But this was a more specific example that I used in detailing some of the challenges of natural language processing. Yeah? There is a list of 5 or 6 different examples. This one is just to take one example of those. So we have information may be split over multiple clauses that use references such as pronouns that may be difficult to resolve. For example, compare the she and both. Jane tried to follow her late grandmother's recipe, but she had not included details of the cooking times. So we can think, who does she refer to there? And Jane tried to follow her late grandmother's recipe, but she had forgotten to buy lemons. Yeah? So which she does she refer to here? And how do we know that? Yeah? So trying to think of an algorithm to resolve this, and this problem is called coreference resolution. This is just one challenge in natural language processing. It looks tough. Yeah? So my introduction to language models or large language models came in this seminar, which was about a year ago. I'm not an expert on large language models specifically. So this was a Dagstuhl seminar. And a lot of people at that time were talking about this weird thing like large language models and GPT, and I hadn't really heard, or I knew something about BERT and so forth, but it wasn't really something I was expert on. So there was quite a lot of discussions at that time. So we formed different groups, and one of the groups with Denny and Kate and Lisa, I think, maybe there were some other people, was to talk about the effects of large language models on knowledge representation, yeah, on this area of symbolic reasoning. So actually, Denny ended up deciding to give a similar talk at a similar, with a very similar title, which I tried to not watch until I prepared my own talk, so I didn't. But essentially, with a very similar message to this one. So again, he was also inspired to give this talk about the future of knowledge graphs in a world of LLMs. Yeah, it's also there's a video online on YouTube of this if you're interested. So the problem with the motivation I mentioned earlier is ChatGPT. Yeah, so how does this motivation hold up if I say that natural language is difficult to process? And now we see that with ChatGPT, we have a very real demonstration that that may not be the case. Maybe we can process automatically natural language. So I tried with my first, and I know it's a bit cliche to show examples of ChatGPT and so forth, but this ties in with the example we've seen thus far. The first thing I tried on ChatGPT when I had access, this was after the seminar, this was maybe at the start of this year. So I tried to ask ChatGPT the following. Jane tried to cook her late grandmother's recipe, but she had not included details of the cooking times. Who forgot to include the cooking times, Jane or her grandmother? So what do we think as humans here? Grandmother, yeah? And indeed, ChatGPT was quite certain or specific. Jane's late grandmother forgot to include the cooking times in the recipe. So I thought, oh, okay, 50-50 chance, that's interesting. How about this one? Jane tried to follow her late grandmother's recipe, but she had forgotten to buy lemons. Who forgot to buy lemons, Jane or her grandmother? Jane, in this case, we would think. And ChatGPT also agrees. Jane forgot to buy lemons in this case. So basically, the motivating example of this book that I had happily published and thought maybe would hold up for at least 10, 15 years was now gone. Yeah? And I tried further examples, and yeah, okay. And then eventually, it did very well. And then eventually, I wanted to figure out how it was concluding this, and I just asked, why was Jane's grandmother late? So in English, maybe if you're not a native speaker, late grandmother means passed away, has died, basically, in the setting. Yeah? So why was Jane's grandmother late? And then ChatGPT says, I don't know why Jane's grandmother was late. Maybe she missed the train. Maybe it was raining, whatever. It still had this idea somehow that Jane's grandmother was tardy, as in late in time, right? Not that she had died. So it was sort of, okay, it's not certain how it arrived to the answer, but it got to the correct answer earlier, but it clearly doesn't really understand what's going on here, yeah, and as we would as humans. So then I insisted, Jane's grandmother had passed away, why was she late? And basically ChatGPT was, yeah, it's still like saying, oh, I'm sorry, but you didn't mention anything about why she would be late, yeah? So just to mention, I tried later with GPT-4, and GPT-4 figured exactly what was going on. Yeah, so with ChatGPT using GPT-4, it said, yeah, late grandmother typically means that she's passed away. Okay, any questions or doubts so far? Or any? Keep going. So I think it's interesting then to provide a bit of kind of past perspective on this ChatGPT phenomenon, which people are still trying to understand. I'm still trying to understand. Nobody knows really what's going on with these emergent capabilities of these large language models. And people are sort of really shocked by this. But this isn't the first time in history people have been shocked by some development like this. So maybe one of the original artificial intelligences that we could talk about was the following. Does anyone recognize this? You probably have heard of the name of this, even if you haven't heard of this specific element or of this specific setup. This is Mechanical Turk. Yeah? So this was developed in the 1780s, if I remember correctly, and basically it was an automaton that was designed to automatically play chess and was capable of beating the best chess players. Yeah? And people were wondering how a machine could be so intelligent, right? The answer to that was very simple. There was a guy inside who was hidden away, and they used mirrors and all sorts of tricks, and they would open the doors and there was nobody inside, and then the player would slide forward and the person inside was an expert chess player. And they used magnets to mirror somehow the player's movements with the real movements. So people were like blown away by this. They were like, how is this working and so forth? But okay, in this case, it was a trick, right? Artificial intelligence largely started around the time of 1955 with this Dartmouth workshop. So workshops in those days were a bit different. It wasn't just go somewhere for a week. In this case, the proposal was to have a 2-month workshop with 10 people, 10 men, in this case, less politically aware, let's say, to study artificial intelligence to be carried out in 1956. And the study is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. So at the start of AI, there was a lot of focus on rules, on symbolic approaches like we saw. Yeah? Break things down into symbols, simplify them, define rules, and then process those symbols. What's interesting is that they were quite, how would I say it, optimistic. So in terms of artificial intelligence, we think that a significant advance can be made in one or more of these problems if a carefully selected group of scientists work in it together for a summer. They had the idea that they would that summer solve artificial intelligence. Yeah? I mean, those of us who've written project proposals have seen similar such optimism at times, but okay. So what specifically were they working on? Automatic computers. If a machine can do a job, then an automatic calculator can be programmed to simulate the machine. The speeds and memory capacities of present computers may be insufficient to simulate many of the higher functions of the human brain, but the major obstacle is not the lack of human capacity, but to use the current capacity efficiently, basically. So this is kind of interesting that they were stating this in 1955 when the proposal was made. How can a computer be programmed to use a language? It may be speculated that a large part of human thought consists of manipulating words according to rules of reasoning and rules of conjecture. Forming a generalization consists of admitting a new word and some rules whereby sentences containing it imply and are implied by others. So they were interested in natural language processing from a symbolic rule-based perspective. Neural nets. Yeah, so for people who think that this deep learning stuff is new, it kind of is, but it's not. It's just bigger with better machines and lots more data. They spoke about how neurons could be used. Self-improvement, how machines could iteratively over time improve themselves to get better at a task. Randomness and creativity, I've jumped a couple that were maybe not so relevant, but randomness and creativity, this idea that creativity is logical, but basically inserting randomness occasionally to come up with inventive ideas. Yeah? So what's interesting is how correct they were about a lot of these concepts, but how long they were far too optimistic about how long it would take to develop systems and algorithms to actually satisfy this. I'm not going to go through every year, but a major or seminal paper as well in terms of machine translation, in terms of translating languages, in this case from English to Russian. This was a paper in 1955. Which focused on trying to create an algorithm to translate 10 Russian sentences into English. Yeah? So it was trying to say, okay, let's just create what algorithm would work well just for these cases. Yeah? So what was the proposal? It was basically this algorithm here. Yeah? So the author was quite satisfied that if you had a good enough algorithm, you could just take one language and then apply your algorithm, and then out the other side comes this other perfect language. Yeah? Now, this is a hypothesis that was largely rejected over the following 10, 15, 20 years. Yeah? So continuing, we have ELISA. ELISA was from 1966, and it was a chatbot. It was, okay, I'll maybe describe how it works later. You can still find some implementation of this. So this was implemented in the 60s. So I am in. This is the jet lag is kicking in. That's why I can't type well. Do you believe it is normal to be Aiden? Why no? Okay, that wasn't the best session. Okay. We can, you can try it if you want. This is basically, you have to, again, think this was coded in 1968. 66, sorry. So what was the idea? The idea was that, again, ELISA was sort of a trick. Elisa was using a Rogerian psychotherapist type model. What is that? It's basically responding to an answer with a question. Yeah? So it's basically, I'm sad. Why are you sad? I'm sad because I lost all my money. Why did you lose all your money? And it continues in this way. And people tend to be self-directed. So they think that somehow they're having an interesting conversation with a human. And people really thought this is almost a human-like chatbot, when really they were pleased by the attention that the algorithm was showing in their problems and their life. So, So now this brings us, we skip a lot here of developments and so forth of modern machine learning and the move away from expert systems and symbolic approaches towards more induction, towards machine learning. And we're moving back to ChatGPT. Yeah? So Pandora's box, we could maybe describe it. So how does it work? Very briefly. I'm not going to get into details, but somehow this model was trained on Wikipedia, on Common Crawl, which is this massive open access crawl of web pages, basically web content, and various corpora of books. So what is the task? What is it trained for? Basically, the goal or one of the benefits of ChatGPT, or the GPT, I should say, the GPT language models, is that we don't require labeled data. We can just take text and then we can try to train a model for this task. Yeah? So we can train a transformer-like model using attention to try to address what is the next word in this sequence of words. Now, ChatGPT doesn't use, or GPT doesn't use words, it uses tokens, which can be subword. However, in this case, what we're going to produce is some sort of distribution probability maybe in inverted commas, distribution over what are the most probable words. So we could say my favorite movie is The Last. And we could say that the most probable is last of something, or we could say last airbender, emperor, samurai, and so forth. This is essentially what these models are doing. Yeah. Then we have all these different large language models that have been produced. We have GPT, GPT-3, 3.5, 4. We have Palm from Google. We have Llama 2 from Meta. We have Bloom, which is an open source effort by the Hugging Face, what's it called? People. And we have Pangu Sigma, which is from Huawei, for example. And there's more. Yeah. So what about ChatGPT? Then ChatGPT has this additional element where it takes this language model, it takes a bunch of people, and then it basically creates a chat interface with these people, and it receives feedback from these people. Yeah. So it's essentially reinforcement learning based on human interaction. Yeah? So taking these people and asking them, did you like this response of ChatGPT or not? Yeah. So this is what we're contending with. So the question now, and many people were asking this, is, okay, with LLMs, with their inherent capability to answer complex questions, to process and to understand, I put in quotes, natural language, is there even a need to structure data anymore? So for example, or even papers, this quite dramatically titled paper, language models sounds the death knell of knowledge graphs, which for me is quite worrying because that's my profession. I've spent many years becoming an expert in this topic of semantic web and knowledge graphs. So before we go off and write signs because we're going to be out of a job, I think it's important to highlight that still there are problems with GPT. Yeah. So some of those are known. Yeah, so some of them will be quite familiar. Maybe if you've heard of GPT, you will have heard of it. The contrast isn't so great here, but okay. Hallucinations, it sometimes makes stuff up, stuff that's not even in the training data, because it's better to make something up than to not say anything sometimes, although sometimes it will say it doesn't know. Opaqueness, it's hard to understand why we get certain results from large language models. Intransigence, which means basically that it's just difficult to change an LLM if it's, the results are incorrect. Where do you go to fix that? It's not really clear. Staleness, so LLMs are trained infrequently and it's a very expensive task to train them, so it's difficult to get regular updates. Bias, so LLMs can exhibit bias from training corpora. Costs, LLMs are costly for training and for inference. Short tail, LLMs do not work well on rarely discussed topics. They're great for things like actors and movies and books and novels and so forth. But you ask questions about biology or astronomy that are not so discussed on the web, it struggles, although of course that's a question of the training data. If you selected more documents from those domains, it should work better. Sanitized, so LLMs are somehow restricted to ensure that they don't provide dangerous sorts of output, which is a feature but also an issue, because if you want to do certain types of research that involves these sorts of topics, ChatGPT will probably tell you no. And non-determinism, that the outputs of large language models are time or language or prompt sensitive. Yeah, so there's a lot of people saying ChatGPT got dumber at some point because there was so much demand that it was using less compute time for each request. So as another example of ChatGPT in terms of some of the limitations, some of the hallucinations are, you have to force them somehow to create an hallucination, but in the course of Web of Data, where I teach the semantic web, in the first lab, I give them some questions that are difficult to solve using the web. And this question is, which Turing Award winners were born in Latin America? Very simple question. Yeah. So in the case of ChatGPT with GPT 3.5, it invents a winner. So Adolfo Guzman Arenas never won the Turing Award. And it clearly states that Adolfo won the Turing Award. What's interesting is that the person who did win the Turing Award and was born in Venezuela, Manuel Blum, is mentioned, but not as the winner, which is kind of strange. GPT-4 basically says, I don't know of any Turing Award winners who were born in Latin America. Yeah? So there is an answer, which is Manuel Blum. However, what's interesting is if we ask for a Sparkle query to find the Turing Award winners, this is the most impressive part of ChatGPT for me, is its ability to produce JSON data, programs, queries. I have no idea how it gets this, but essentially now it generates a Sparkle query that we can try in Wikidata and it loads, to find the Turing Award winners who were born in Latin America. And it does a surprisingly good job. So we have award received here, and we have this unnecessary reification, but this still works. And then we have this entity here, which is Alan Turing. Not the right entity, right? So Alan Turing is not the Turing Award. So we can change that. But OK, we see how it made that mistake. So the award received should be Turing Award. Yeah. So we have end time, which we don't need, but fine. Doesn't change the nature of the query. We have person was born in. I don't know why it's not showing me this, okay, but this is birthplace. And then we have birthplace continent, and then instead of Latin America, it puts, what's up? Big Brother. Okay. A little bit strange, but we can change this to Big Brother, or we can change this to Latin America. Now, this is unfortunately due to another problem with knowledge graphs. If I run this, I think I changed everything, didn't I? Yeah. If I run this, this is going to time out. Or no? No, it's not going to happen because it has no end date. Actually, I need to remove this, and then it will time out. That's not ChatGPT's fault. No. Award received. OK, let me just do this. I'm going to remove this verification, and it's not continent. Because it's Latin America, and Latin America is not a continent that should be part of. No. Please, I have 2 columns. This time, please. No. One last try. Word received. Place of birth. OK. So let's say. No. So we get the country of the place. And now it's going to time out. Let's see. OK, we could maybe leave it and then return. No, we have the result. Manuel Blum was born in Caracas. So the query wasn't perfect, but it's quite impressive. It's quite impressive that it knows the P's and the Q's of Wikidata, particularly the P's, not all the Q's, not all the entities. But this is very promising for me. This idea that maybe instead of asking LLMs for answers directly, they can generate queries against structured data. Yeah, because that structured data is curated, and it has somehow some process of truth and some notion of truth behind it. It's not just creating the most likely tokens or using this sort of model to come up with something that will satisfy the user. So this idea of somehow LLMs and KGs, rather than defeating or making knowledge graphs redundant, maybe together they can be a dream team. So we can think of ChatGPT, but maybe we can turn it into something more like this, where we have some sort of graph structure within it and somehow hybridize the two worlds, yeah, to have a LLM plus KG. So if we look at the downsides of LLMs that we previously discussed, hallucinations, opaqueness, and so forth, we see that KGs in general don't suffer from these sorts of problems. Actually, they work quite well in these sorts of settings. So KGs don't suffer from hallucinations. KGs are not so opaque. We can go to Wikidata and see where is the birthplace of Manuel Bloom. If we don't like it, we can change it, so it's not so intransigent. Staleness, okay, maybe that is a problem for KGs, but at least we can go in and change the data in Wikidata if we want at any time. Bias as well is still a problem for KGs, but it's somehow addressable. The cost of LLM for an inference, oftentimes it will take about half a second or something to find out some basic fact, like who is the president of Ireland, let's say, or who's the president of Chile. In the case of a KG, it's a fraction of the cost. It's a tiny cost because it's just a lookup. We're not trying to infer something from a model, yeah? So costs should be, in general, more efficient for KGs. As we saw, that sometimes we have timeouts, but still an issue. So short tail, in this case, KGs should be better for domain-specific data. Yeah. Sanitized, which means that, okay, we can talk about controversial topics if in a factual way in KGs, which is somehow difficult with language models. Non-determinism, if we run the same query, we would assume the same data or the same answer should be returned. However, there are some advantages to LLMs that could be very interesting in the KG setting as well. The first is usability. Yeah? It's very nice to be able to put in some text and not have to write a Sparkle query. Yeah? It's very nice to put in your question as a text and get some answer, and that attracts a lot of users. And the other aspect is that KGs are good in general at answering factual data, but not in giving advice or recommendations or maybe instructions on how to do something. Yeah? So in this sense, LLMs can answer. And a lot of questions that if you look at a web search engine, they're not searching for specific facts. They're searching for how do I do this? Or what would you recommend for X? Yeah? So these are interesting aspects. And then we can add another column for what happens with the combination of KGs and LLMs. Yeah, what can we get out of this? So we could be optimistic and say green thumbs up for everything. We could be a little bit more constrained and take the best and say green, green, green. Gray, 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 green, 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 thumbs up for these. Yeah, we can take the best of both. It's not really clear, yeah, what we could get out of this combination. So I just very, very briefly, because I know time is also, we're coming up on time. I did kind of a small search because I'm sure there are people working on this topic of combining language models, large language models, GPT, ChatGPT with knowledge graphs. Yeah, so I did this sort of kind of limited, informal, not very thorough survey to get an idea of some works out there, and found works on these 6 topics. So there's works on training models that combine KGs and LLMs. So somehow mixing KGs and LLMs during the training phase to create a model that might involve specific layers for knowledge. It might involve annotating the text beforehand with knowledge graphs so it recognizes tokens from, let's say, Wikidata. Decoding LLM knowledge as knowledge graphs, second topic. So this is essentially the idea of how to get the knowledge that's somehow implicit in these LLMs, how to extract that as a knowledge graph. There's some work on that. Verbalizing KGs using LLMs. So given a knowledge graph, describe it to me. Tell me what this says in human language. Hybrid KG LLM tasks. So in the case of query or question answering, there is this sort of 2 tasks that are in parallel worlds. There's one task which is natural language processing or natural language question answering, which is given a question, answered. And there is a version for structured data, for example, for knowledge graphs. And now people are looking at how to mix these 2 different types of tasks. Yeah, so query, question answering. We have LLM-enriched knowledge graph tasks. For those who know knowledge graph or do research in that, you might have heard of knowledge graph completion, which tries to find new edges. Knowledge graph construction, which is basically information extraction, given text, extract some edges. KG summarization, which is find an important key summary or core of the knowledge graph. And people have also looked at various tasks using LLMs for knowledge graphs. Then there's a bunch of surveys, discussions, and experiments. So there's some interesting discussion there. One of the things I found was this taxonomy of work on LLMs meet knowledge graphs is still not published. The ones with asterisks are just on arXiv. They're not peer-reviewed published. So it gives this overview of basically at the first level that we have knowledge graph enhanced LLMs. So we take an LLM and we use a knowledge graph to improve it. We can have LLM augmented knowledge graph. So we have a knowledge graph and we take an LLM to improve it or make it somehow better or more flexible. And then we have this more synergized sort of balanced approach where the LLM and the KG are somehow at the same level and we're trying to integrate them and hybridize them. There's also work on another survey if you're interested in more details. This is again just on arXiv. It's very recently published. A lot of these papers have emerged on arXiv in the last few months. So this is kind of like very recent stuff, still not peer reviewed. This is a discussion of how to integrate or use knowledge graphs to enrich the training process, the training of large language models. So there's a discussion of before training enhancement, during training enhancement, post-training enhancement. It talks about different techniques and provides a survey of these techniques for how knowledge graphs could be used to improve the training of large language models. So I just wanted to mention those two because they provide a synthesis and a survey that can go in more detail for those who are interested in more details. So my personal view of this and my takeaway to start to conclude is that LLMs can make knowledge graphs more usable. I think this is one of the, it's not the only use case, but it's one of the use cases that I'm most excited about in the integration of knowledge graphs and large language models. So about 4 years ago, I did, in the context of the semantic web, a survey about what people thought were the main problems associated with the semantic web. This was 20 years on. And basically, if you see the darker blue values, the darker blue values to the left mean that people are more worried about this topic. And lighter values mean people are on the left, mean that people are less worried about the topic. Yeah? So one thing that really sticks out as things that people were worried about in the context of the semantic web was this idea of unreliable publishers or unreliable data, not being able to trust or use data that's published. Lack of incentives. Why would people go to the semantic web? Why would they publish data? Who's going to pay for this? And so forth. And another element that was probably of all of the criteria, number 9, lacks usable tools. That there isn't enough usability in the semantic web setting. It's too hard for people. It's too difficult to engage them. So this was people's main concern was usability. Yeah? And this was of the survey. I think there's about 120 respondents or something like that in this survey. So in this case, a solution to this could be these large language models. Yeah? We could view these large language models as a tool to address this lack of usability that has existed for a long time. And as a simple conceptualization, basically when we talk about knowledge graphs, often we can talk about data, query, and a logical layer. Yeah? So logic can be rules or ontologies. We have queries, for example, in languages like Sparkle or Cypher. And we have our data in an RDF format as a graph or as a property graph or what might you have. So what we could add then is just basically this language layer that's somehow transversal and that allows users to talk with it and to interact with the data, the query, and the logic layer. Yeah? To ask questions that already exist, or maybe to ask that additional details are added. For example, given text to find new data, to find new rules, to find new logic, to write the queries for them. Yeah? And this would address this major issue for knowledge graphs of usability. In general, that if we address the question of usability for knowledge graphs, then we could somehow also attract lots of users to use these sorts of services. So if we look at Wikidata, for example, people are editing Wikidata, but they tend to be hobbyists. Yeah? People mainly read the Wikipedia article. They don't go on Wikidata. Yeah? So Wikidata has lots of used applications. But these also use a language layer. For example, Wikidata is thought to be used for Siri and Alexa and so forth as an important source of knowledge. It's also used by Google or as part of Google Knowledge Graph. With this usability, if we could address this usability, then knowledge graphs could be used by more and more users. So in terms of conclusions, some key points, I would say LLMs certainly solve some tasks that knowledge graphs do. LLMs do not replace knowledge graphs. Knowledge graphs here as well, just to mention, we could subtract knowledge graphs and say structured data, or this idea of structuring data. We could talk about relational databases and advantages and disadvantages of JSON, XML graphs, but that's another discussion. Knowledge graphs are nice and flexible. Now, LLMs likely will never replace knowledge graphs. LLMs plus knowledge graphs are an interesting research topic, and one that's probably likely to grow very, very quickly. LLMs can make knowledge graphs more usable and bring them to the masses. In this case, I would say probably if this happens, it will be seen as an LLM. So if you take LLMs and KGs, people will see the LLM, they won't see the KG, and they won't know what a KG is, and that's fine. The application or the tool or the technique will be better. This has happened a lot with the semantic web. Yeah? Nobody knows about the semantic web, but you all use the semantic web every day, which is another, you can see the first class of my lecture on this. I think 60 or 70% of websites now have RDF data. Yeah, and that's fine, that's okay. If people are not excited when you say knowledge graphs, or if they're more excited when you say a large language model, that's perfectly fine. Yeah? But knowledge graphs can be doing a lot of work in the background. This was a meme, I'm not sure. I was working on it towards the end, so classic meme from Monty Python. Core idea is that knowledge graphs are not dead yet, so that's good news. We still have some work to do. Yep, that's it. So thank you very much.